Right, I'm going to go ahead and start. I'm going to say a little bit about tomorrow's lab. It's in the Williamson hardcover textbook. It's chapter 20. It's called Bromination, Debromination of Cholesterol. Okay, this is just a partial structure of cholesterol. Okay, it actually contains 2 more rings and some other substituents, but we're focusing here on the double bond. All right, so this is an addition reaction. The double bond will attack bromine. Okay, so we'll form this 3-membered ring, and the ring will actually be underneath because there's a methyl group here that interferes with addition on the front side. Okay, that doesn't make too much difference as far as experiment. I'm going to go ahead and erase this. So we'll go back this way. Okay, so a bromide, Br minus, will then attack this side. Again, there's a methyl in the way. Okay, so that's going to break open the ring. Okay, let's do it this way. Okay, because of that 3-membered ring, the 2 bromines will be trans. And it turns out because of the ring structure, they'll also end up anti to each other. Okay, so that's the first part. And you're going to, then you're going to collect the dibromo cholesterol. Okay, the overall purpose of this lab is to purify commercial cholesterol. Cholesterol in the bottle contains some very similar compounds, and okay, one of them has no double bond. One of them has a double bond in a different place. One of them has 2 double bonds. Okay, so these minor impurities, okay, whether they're brominated or not, they're going to remain in solution, and this dibromo will precipitate out. Okay, they may not be particularly soluble, but there's such a small amount that they remain in solution. And so you're going to remove those impurities during the recrystallization process. Okay, so this will crystallize out. Okay, so that's an electrophilic addition to an alkene. And then the second part is the debromination. Okay, there are two common reagents that are used for debromination. Okay, one is sodium or potassium iodide. Okay, which we won't be using. But what happens here is the iodide attacks one of the bromines, forms a double bond, kicks this out. Okay, so that gives us back our alkene. Okay, what class of mechanism is this since we're getting a double bond and everything's happening all at once? E2, good, that's an E2. Okay, what we are going to use though is zinc. All right, the configuration of zinc, electron configuration of zinc for the valence electrons is 4s2 3d10, and it is these two 4s electrons that zinc uses to attack the bromine. Okay, and this is also an E2. Okay, so that will give us back our double bond. Okay, and then the cholesterol that we obtain will be more highly purified. The impurities, there's not a huge amount of impurities. They may be 1 or 2%. But these are removed during the recrystallization. Okay, as this precipitates out, the byproducts will remain in solution, and then we do a suction filtration to isolate this. What's that?
Yeah, a few people on the waiting list.
Oh, okay, sorry. Yep. Okay, let them in. Okay, so we have an electrophilic addition. We have an electrophilic addition of bromine to an alkene, and then we have an E2 elimination using zinc. Okay, in the process, zinc also gets oxidized. So, okay, because we'll be doing this in acetic acid, we'll get zinc acetate. Okay, as far as precautions, okay, I'll repeat this briefly tomorrow as well. There are, in particular, two substances that we'll be using that are corrosive and irritating. Okay, one of them is bromine. Okay. You may or may not be familiar with the odor of bromine, but you're probably familiar with the odor of chlorine. Okay, if you've used chlorine bleach, or if you've gone to the swimming pool. Okay, chlorine has a sharp, irritating odor. Bromine has a somewhat similar sharp odor. Okay, so it will burn your eyes and your nose, so you want to make sure that you don't breathe it. Handle it in the hood. Okay, also the other main hazard is acetic acid. Okay, so if we're using glacial acetic acid, that is the concentrated stuff. Okay, vinegar is about 4 to 5% acetic acid. And this is the 100%. What's especially hazardous about acetic acid? First of all, the odor is irritating if you get it up your nose, but also unlike some other acids like hydrochloric acid, you get hydrochloric acid on your skin, you know it right away, okay, because it'll immediately start to burn. Acetic acid will seep through the oils of your skin over a period of several minutes. You might not feel it at first, but then after 15 minutes or so, it will start to burn like crazy. So if you do spill acetic acid, make sure that you wash that off. Okay, we'll be doing the microscale version. Okay, so this is chapter 20 in the Williamson textbook. Okay, next I'm going to share my screen. We'll pick up where we left off last time. Okay. For some reason this takes a while to load. There we go. Okay. Share my screen. All right, so we have looked at hydration, halogenation, halohydrin formation, HX addition. Okay, we just got started on cyclopropanation. Okay, we talked about some of the methods of cyclopropanation. We'll look at epoxidation and oxidative cleavage and dihydroxylation. Okay, regioselectivity, that's when a reaction prefers a particular positional isomer. With addition of HX, the rich get richer when it comes to hydrogen. Okay, so hydrogen goes to the side that already has the most hydrogens. Okay, and the reason is the more stable carbocation is formed in the intermediate stage. There are two anti-Markovnikov reactions. One is the free radical addition of HBr, so HBr and peroxides. Okay, that actually gives us the reverse or anti-Markovnikov product. Okay, so the side which has the fewer hydrogens gets the hydrogen. And the reason is that the more stable free radical results for the intermediate. Okay, this does not work with HCl or HI, only HBr. Okay, so this is the anti-Markovnikov product. If we were to add HBr to 1-methylcyclohexene, hydration is when we add water in the presence of an acid catalyst. Okay, this is just the reverse of what we did a couple weeks ago in lab. You have protonation of the alkene, water adds, water removes a proton. Okay, so that regenerates the hydronium ion. Okay, this follows Markovnikov's rule. Rearrangements, not only with hydration, but also HX, are possible. Oxymercuration, demercuration. Okay, the main thing I want to repeat about that is it forms the Markovnikov alcohol, but it prevents rearrangement. Okay, because of the three-membered ring, the mercurinium ion, this prevents methyl or hydride shifts. Okay, if we use an alcohol instead of water as our solvent, we'll get an ether rather than an alcohol. Hydroboration is the other anti-Markovnikov reaction. This uses diborane or borane THF. Hydroboration is also stereoselective. Okay, H and OH are added syn to each other to the same side. Okay, addition of halogens. Okay, I just showed you this a few minutes ago. This is one of the reactions we'll be doing tomorrow. Okay, so a halogen adds to form this three-membered ring, a halonium ion, and then the halide attacks to give you the anti-addition of the two halogens. Okay, so if the alkene is part of a ring, the bromines will be trans. If the halogen is in water rather than in a nonpolar organic solvent, then we get a halohydrin. Okay, this is both regio and stereoselective. OH will end up on the more substituted carbon, and it's stereoselective because the halogen and the hydroxyl group will be trans to each other. Okay, and here's an illustration of the regio and stereoselectivity of halohydrin formation. Okay, we go through the bromonium ion. Water attacks the more substituted side, the side with the methyl group on it, and it attacks from the opposite face. Okay, so bromine is back here, so the water comes in from the front, and so the alcohol and the bromine will be trans to one another. Okay, this is a completely different mechanism. It occurs at the surface of a heterogeneous catalyst. This is hydrogenation. And it is stereoselective. We get the two hydrogens added cis. Okay, this is a homogeneous catalyst. It's a soluble catalyst for hydrogenation. Okay, carbenes. Three ways to generate carbenes: diazomethane, the Simmons-Smith, and alpha elimination. The diazomethane, when it's decomposed, forms this methylene carbene. nitrogen gas. Okay, but it has some disadvantages. It's toxic and explosive. Simmons-Smith is a much better method. Okay, this forms a cyclopropane ring across the double bond. Okay, alpha elimination. Okay, if we have a haloform or a trihalogenated methane, that remaining hydrogen is acidic enough where some of it can be removed by hydroxide. Okay, so we get this anion, and then this anion spontaneously kicks out a bromide, in this case, giving us our carbene. Okay, the carbene has an empty p orbital which accepts a pair of electrons from the alkene, and then it has this pair of electrons in an sp2 orbital which donates. So it accepts and donates and forms a three-membered ring. This is stereo specific. The cis or trans stereochemistry in the alkene is maintained. So here we have a trans alkene. The two phenyl groups will be trans in the product. Okay, if they start out cis, they'll be cis in the product. The Simmons-Smith and the alpha elimination are both stereospecific. Okay, the alpha elimination, of course, will give you a dihalogenated cyclopropane. Okay, this is where we left off. Epoxidation. Okay, if we use a peroxy acid, okay, this will add an oxygen across an alkene. Byproduct here will be a regular carboxylic acid. Okay, and it's this oxygen that gets added. One of the most common reagents for epoxidation is this one. It's called MCPBA. Okay, which stands for metachloroperoxybenzoic acid. Okay, this is a good choice. It's soluble in a lot of the organic solvents that we use. Right, here is the mechanism. Okay, it goes through this cyclic transition state. All right, this oxygen closest to the H, okay, accepts a pair of electrons, and then this pair of electrons gets donated. This bond breaks, forming a double bond here. This is the transition state. We form an epoxide, and our byproduct is a carboxylic acid. Okay, this reaction, like the carbene formation or the cyclopropane formation, is stereo specific. Okay, if we start out with cis, okay, our product will be cis. Okay, so both the CO bonds are added to the same side. Okay, and then if we start out trans, the two methyl groups here will be trans. Okay, there are various ways of opening an epoxide ring. I'm planning to talk about ethers a little bit later on in the semester. Ethers are generally chemically unreactive. Epoxides, though, are an exception because of the ring strain of the three-membered ring. Okay, they undergo ring opening reactions. And here we'll talk about the acid catalyzed process. All right, so the first step is, okay, if we have a little bit of acid catalyst, the oxygen picks up a proton, and then water attacks, and then another water removes this extra proton. We get a trans diol. Okay, because water attacks from the opposite side, okay, the two alcohol groups are trans to each other. Okay, we can get both enantiomers because water could attack from either side. Okay, so this is called an antidiol. Right, these are some of the reagents for epoxidation. Peroxybenzoic acid. Okay, this is peroxyacetic acid. The difference here between the benzoic and the acetic acid is that with the peroxybenzoic acid, we can stop at the epoxide. Okay, with the peroxyacetic acid, okay, because that has a lower pKa, okay, it's more acidic, we don't isolate the epoxide. It just goes all the way to the diol. Okay, here's MCPBA, which I just showed you on the board. That's stereospecific. It gives you this is a trans alkene, so it'll give you the trans epoxide. Peroxyacetic acid will take you to the diol. Okay, remember that when we formed an epoxide and we opened up the ring, okay, remember that the two alcohols were trans or anti to each other. Okay, what if we want a diol in which they are cis, or the process is one of syn addition? Okay, there's two main ways of doing this. This is, we can use osmium tetroxide and hydrogen peroxide, or we can use potassium permanganate in basic solution. Okay, OS, that's osmium, it's element number 76 in the periodic table. Okay, notice it has an unusual oxidation state. It's +8. Each oxygen is -2, so by difference, osmium is +8. Manganese and potassium permanganate is +7. Conditions are important here for the permanganate. We need to use a cold dilute solution of KMnO4 to carry this out. Okay, so when we use osmium tetroxide, also known as osmic acid, that forms this osmate ester, this 5-membered ring. And then you use a secondary oxidizer like hydrogen peroxide, or let's see, I've used this other one. Yeah, I've used this as a secondary oxidizer. Okay, you can do it without the hydrogen peroxide or the tertiary amine N oxide, but you'd use up the osmium tetroxide. Osmium is it's a rare, expensive metal. Okay, it's down there at the bottom of the periodic table with gold and platinum and some of those others. So it's rare and expensive. Okay, this regenerates the OSO4. Okay, and because of this osmate ester, this helps to explain why the two alcohol groups are syn to each other. Okay, so we get a cis glycol or cis vicinal diol, and then that regenerates. Okay, this is very similar. This is with cold dilute alkaline potassium permanganate. Okay, we form a similar intermediate, this manganate ester in a 5-membered ring. And then when this breaks down the presence of hydroxide water, we get the cis glycol. Yeah.
Why does that have to be cold?
What?
Why does that have to be cold?
We'll actually see what happens when it's hot. It will actually split the carbon bond if it's warm. Okay, the question was, why does it have to be cold? Okay, so here's your answer. If the solution is warm or acidic or too concentrated, oxidative cleavage of the glycol may occur. Disubstituted carbons become ketones. Monosubstituted carbons become carboxylic acids. Okay, went the wrong direction. Okay. So instead of cold dilute, here we're using warm concentrated. We form the glycol, but then it splits, and it will form into a ketone, and then the aldehyde is oxidized to a carboxylic acid. Okay, so in this example, we have a hydrogen here. So it's going to split this double bond, and wherever you have a carbon-carbon double bond, it will split that and you'll form 2 carbon-oxygen double bonds, okay, which is what we have here. Okay, so we'll split this, we'll get the ketone. There was an H here, but then it got oxidized to the OH. We'll get a ketone carboxylic acid. Okay, here we have 2 double bonds. Okay, we're going to split both of them. So we'll split this one. The single carbon here gets oxidized all the way to carbon dioxide. Okay, so we'll form a ketone here, carbon dioxide here. And then since this alkene group was part of a ring, we'll split it and we'll open up the ring. And since we had two hydrogens here, we'll get 2 carboxylic acids. Okay, so this is an example of what is called oxidative cleavage, okay, where you actually break the carbon-carbon bond. Okay, another way of achieving oxidative cleavage is to use ozone. Okay, ozone is a allotropic form of oxygen. It's O3 instead of O2. Unlike ordinary oxygen, which is odorless, ozone has a pungent odor. Okay, so at minus 78 degrees Celsius, that would be a dry ice acetone bath. Ozone splits the alkene, and then we use a reducing agent such as dimethyl sulfide. Okay, so we have 3 oxygens in ozone. One goes here, one goes here, one goes with the sulfur. This is, and we go from dimethyl sulfide to dimethyl sulfoxide. Besides dimethyl sulfide, you could also use zinc, okay, which would give you zinc oxide, ZNO. Okay, so ozone, right, if I draw the Lewis structure here, so ozone can accept a pair of electrons and it can donate a pair of electrons. Okay, so it forms this, what's called a malozonide at first, and then that rearranges to this ozonide. And this is never isolated because the intermediate is explosive. You want to reduce it right away. So you don't want to isolate these intermediates. Okay, so you get this ozonide, and then either zinc or dimethyl sulfide will reduce. Okay, notice the difference here between the potassium permanganate and ozone, and that is that we do end up with an aldehyde as the final product. Okay, if we were using permanganate, this aldehyde would go on to become a carboxylic acid. Okay, so here's a comparison of permanganate cleavage and ozonolysis. Okay, the warm concentrated permanganate, again, will split the double bond. The ketone and aldehyde are not oxidized. The aldehyde immediately goes on to the carboxylic acid. This is a carboxylate since we're doing it in basic solution. Okay, with ozone though, and reducing second step, okay, we can get the aldehyde. So that's the main difference here. But they'll both split a carbon-carbon double bond and give you 2 carbon-oxygen double bonds. Okay, so the problem here is ozonolysis reduction of an unknown alkene gives an equal molar mixture of cyclohexane carbaldehyde, which is shown here, and butan 2-O. Okay. So to solve a problem like this, okay, what you should do is line up the oxygens. Okay, if you have the oxygens facing each other, okay, so here we're working backwards. Okay, these are the final products. Okay, so if you erase the 2 oxygens, reconnect, okay, there's your alkene. Okay, and in this particular instance, the alkene could be E or Z. Okay, either one would work. Right, another reaction of alkenes is polymerization. An alkene, which is the monomer, can add to another molecule like itself to form a chain. Okay, the three main methods of alkene polymerization are cationic, free radical, and anionic. Right, in cationic polymerization, in this example, we're starting out with isobutylene. Okay, when the alkene grabs a proton, we get the tert-butyl cation. Another alkene, isobutylene, attacks the carbocation. We form this dimer, okay, which also forms a carbocation. Okay, and then this gets attacked, and so on and so on, and then we get a long chain. Termination can occur, for example, if we have an elimination reaction at one end. If a proton is abstracted, besides sulfuric acid, another catalyst that's used is boron trifluoride. Okay, this is a Lewis acid. It's a good electron pair acceptor. Okay, so water attacks the boron trifluoride, and then styrene picks up a proton from the resulting addition product. We get a carbocation, and another styrene attacks, and so on and so on, and then we get polystyrene. Okay, that's a carbon chain with every other carbon having a benzene ring. Okay, polystyrene is a type of plastic. If it is blown full of air or gas, then you get styrofoam. Okay, and eventually the chain will terminate. Polystyrene and polyethylene are often prepared by a free radical process. Okay, so what we do is we start out with a peroxide, and one of the ones that's often used commercially is this one called benzoyl peroxide. Benzoyl peroxide is also found in several acne medicines. Okay, so just using heat, we split the oxygen bond. We produce these alkoxy radicals. These will break up a double bond to form a new free radical. Another styrene attacks the free radical, generating another free radical. So this is a chain reaction, and so the chain keeps growing. Couple ways that termination occurs. is either two free radicals will pair up, two chains will join together, or sometimes in the process, a radical inhibitor is added to shut down the process. Okay, anionic polymerization. Okay, I'll finish up here. Anionic polymerization occurs in superglue or crazy glue. This is alpha methyl cyanoacrylate. If you have just a trace of moisture, okay, which will produce hydroxide, that generates this anion, which will attack another monomer, generate another anion, which will then attack another anion. And then we get the polymer, and this is hardened superglue. Okay, so I'm going to stop there since we're out of time, and I'll see you in lab tomorrow.